Hello everyone. So today we're going to go over section 4.1, counting principles. So if we look at example number 1, we can see that Hannah has 3 different sweaters for her soccer uniform and 3 different shorts. Now the 3 different sweaters are in red, white, and black. And so the question asks, and the same thing for the shorts as well. The question asks how many different variations of the soccer uniforms are there, and we're going to draw a tree diagram for this one. So we have red on the first branch, and then we have white in the second branch, and the third branch will be black. Okay, and we're going to add in the corresponding letters as well. Let's go ahead and do that here. So we have red, and then we have white and black. And of course, that's just for the sweater. So go ahead and write that in. And then for the second part, we have the same 3 branches for the shorts. So red sweater, red shorts, that's one of the possibilities. And we also have red sweater, white shorts. And of course, red sweater, black shorts. And that is the same for all 3 different sweaters. So we can draw the same 3 branches for red, white, and black. So go ahead and do that here. So the full tree diagram will look something like what we have on the left here. So here we have red, 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 and the second set of R's are for the shorts, and the W's for the white shorts, and the B's for the black shorts. Okay. So once again, these are for the shorts. So if we look at the full tree diagram, at the very bottom we have 9 different uniforms. And another way to consider this is simply 3 choices we have for the sweaters times 3 choices for the shorts gives us 9 uniforms. So that's certainly how we can handle the question with our tree diagram. However, we'll look at one more question where we use a tree diagram. Here we have a toy manufacturer that is making a toy with 3 parts. The top part is either red or blue. So go ahead and draw a color-coded tree diagram for that. So red on one side, blue on the other side. Okay, here. Red and then blue for the other side, B. And then the middle part is either orange, white, or black. So very similar to the previous example. Oops, sorry about that. So just with the top and the middle part, we already have 6 branches. Let's use O for orange. And then like the previous example, we can use W for white. And B for black. And finally, the bottom part may be yellow or green. So we're going to go ahead and add those in. underneath each of the orange, white, and black on both sides. So that's the yellow part. And then, of course, the green on the other side. Okay, it's a little bit crowded here, but that's okay. Okay, and we can use just Y for yellow. So the advantage of using a tree diagram is we know what all 12 of the possibilities will be. As we can see, there are 12 branches here. If we simply multiply the numbers together, we will have the total number of possibilities, but we wouldn't know exactly what they are. Okay, so that's the completed tree diagram. And once again, we have 2 choices on the top part, 3 choices on the middle part, and 2 choices again for the bottom part. And so we have simply 2 times 3 times 2, and that will be 12 different toys. Okay. Again, this is the top part, so red or blue. Second, we have the middle part, so orange, white, or black. And finally, the bottom part could be yellow or green. So the fact that we can simply multiply the choices together to get the total number of possibilities is called the fundamental counting principle, which is listed right here. If there are A ways to perform one task and B ways to perform another task, then there are A times B ways to performing both. And of course, if there are additional tasks, then we just multiply third and fourth number and so forth. Okay. So let's look at more examples here. So we have a luggage lock that opens with the correct 3-digit code, and each wheel rotates from 0 to 9, so that's 10 digits. And so if there are no restrictions and we're just looking for a 3-digit code, then that will be 10 choices for the first number times 10 choices for the second number, and finally 10 choices for the third number, which gives us 1,000 different codes. Okay. So if we were to change the question slightly and each digit can only be used once, then it is a little bit different. We still have 10 choices for the first digit. For the second spot, we cannot choose the same digit again, so we are down to 9 different choices. And then for the third digit, we cannot use the first or the second digit, so we only have 8 choices left. So the total number of possibility gets reduced to 720 codes. Okay. And of course, we can make a question that's even more challenging than that by changing the parameters just slightly. So license plate consists of 3 letters followed by 3 digits, and we're looking at how many license plates are possible. So if there are no restrictions on the letters or the digits, then we have 26 different letters times 26 different letters again times 26 different letters the third time, because there are 3 of them. And then we're going to multiply by 10 for the first digit, 10 for the second digit, and then 10 for the third digit. Now, of course, we can write this using powers, and so we have 26 to the third power times 10 to the third power. And then we can use a calculator to evaluate this, and that will be 17,576. So that's over 17 million different license plates. Okay, so now we can add in some restrictions. Let's say the letters cannot be repeated. Then it's very similar to what we saw from above, and that is we have 26 letters for the first spot, 25 remaining letters for the second spot, and then 24 letters left for the third spot. And then for the digits, there are no restrictions, so we can simply multiply by 10 to the third power here, actually. And then, again, we can just go through with the calculator. Once again, 26 times 25 times 24 times 10 times 10 times 10. And that will give us 15,600,000 license plates. Okay. So as we expect, the number of license plates is smaller. Right, now the third example, this one's a little bit different. It's more challenging. If the first digit cannot be 0 and no digits can be repeated. So in this case, it doesn't say anything about the letters, so we're going to assume that there are no restriction on the letters. So this will be 26 to the third power. And then, now the first digit cannot be 0. So there are 9 non-zero digits. Okay. And for this one, be a good idea to write down why the numbers are the way they are. So the first one is non-zero, or not 0. Now for the second digit, we have one less digit to choose from because they cannot repeat, but we gain 0 back. So we have 10 digits, and then the first digit cannot be used again, so we're down to 9 digits is basically the idea. Okay, so this one's a little bit harder to explain. Just going to write it here. 1 less, but 0 is back. And then finally, for the third digit, we only have 8 choices left. And so once again, we go to the calculator, multiply the numbers out, and we'll get 11,389. 248 license plates. Okay, so those are all the examples that are going to involve the fundamental counting principles. So starting on page 1 and then both the example 1 and 2 and then the try questions. Now for the next example, this counting problem does not use the fundamental counting principle. So let's look at what it says. It says count the number of possibilities of drawing a single card and getting either a red face card or an ace. So probably the best way to do this question is simply to look at what matches the criteria and simply put a check mark next to them. So red face card will be the Jack of Hearts, the Queen of Hearts, the King of Hearts, and then the Jack of Diamonds, Queen of Diamonds, King of Diamonds, and then, or an ace. So this would mean just any ace will do, so there are 4 aces. Okay, so we are actually going to add the first 6 possibilities, so the 6 red face card and the 4 aces together. So there are 10 cards. Notice that unlike the previous examples, we're not multiplying the numbers together, we're just adding them. And that makes more sense to do here. Okay, next part, either club or 2. Okay, so let's change colors here. There are 13 clubs, so imagine these are all the clubs. I'm gonna put check marks next to all of them. So 13 clubs, and then there are 3 more 2s that are non-clubs, and those are to be included. So we have here just 13 plus 3 for a total of 16 cards. So again, for these two questions here, because of the way that they're phrased, we're not multiplying the numbers together, we're just simply adding them. Okay. Right, so that's it for the fundamental counting principle, and that's it for today. So once again, thank you for listening.